Thank you. It's an honor to be here. Thank you for the invitation. And I do have quite a lofty title today, which I probably won't do justice, but at least I can try. First part of the talk, I will discuss about my work, so you get a little bit of a feeling, get my hands dirty and to see what we actually do. And in the second part of the talk, I want to go a little bit into my motivations. Why do I do what we do, and what's behind that? So, but let me first start with a story. It starts with this man, John D. Rockefeller, from late 1800s. He would later become the richest person in modern history, but before that he was just another oil baron in the US. And basically oil business at that time, it was of course before cars and before electric lighting took off, so it was mainly for light oil, or like lamp oil. And it was a messy business. There was no environmental legislation back in the day. So there was a lot of big industrial side streams that were very toxic. They didn't really know what they were. There were just these waste streams that were dumped into the into the rivers nearby. And so for most of the industry, this was just some nuisance that they didn't want to think about it. But for him, he was brought up very strictly, and he believed there should be no waste in personal life and in no business as well. So he strived towards minimizing all of the waste that came in the processes. So he set to also making product out of this waste. And at some point it got so bad, the situation, that actually rivers caught on fire. And so he was pretty much the only person who was in the industry that was trying to solve that. Fortunately, some years later, he came up with a solution, and it was when Model T Ford was unveiled, and he was there with his solution, which was gasoline. So turned out that waste stream was actually gasoline, and it could be used in automotives. Of course, nowadays you can't buy lamp oil the same way that you can buy gasoline. So the tables turned, and he made his fortune in that. And so I see there also this as a really inspiring story, even though there's also the dark side to the story, but there's also some inspiration to be found there. And so today we try to look in the world, what is the gasoline of today? What is produced in vast amounts? What can be turned into profitable products, and at the same time keeping the long range sight, so sort of that we don't end up with the same type of catastrophe. And so the waste streams that we work with are mineral wastes, and they are over 90% of all waste is different types of minerals. And this is just numbers from Finnish industries. And it starts, of course, when you start to mine metals. There is perhaps only 1%, many times only 1% of that mined ore, there's that metal, and the rest 99% is waste. And so what happens is it's ground up to this very fine powder, and because it's so dusty, it has to be stored underwater, otherwise it will blow away with the wind. So because of that, there's thousands and thousands of lakes around the world which are basic toxic waste. It's not so toxic, but it's anyway waste that's stored in these little large ponds. So that's one of the biggest ones. Then there's construction industry, metal and metal products, electricity, and so forth. But the main waste is always inorganic. That's the sort of waste that you cannot burn, right? Because it is there's no carbon in it, basically. So this is our group, Fiber and Particle Engineering at the University of Oulu. It's another 300 kilometers south of here, and Professor Mirja Illikainen is the group leader. And this is the inorganics and material cycles that I represent. So we started in 2012. Was the first project on this sort of circular economy approach to these problems, and it was very difficult to find any industry that would be interested in these approaches. It was just then when the legislation changed, and all of a sudden we found a lot of industries that were making the waste, basically, that wanted to get rid of that. And just in the last 2 years, it has been also the sort of producing end of the industry that's been asking us for a solution. How can they use somebody else's waste in their products? So there has been a massive change in attitudes in the companies, how they think about waste, how they think about circular economy, and how they could make a profit out of that. And it has a lot to do, or it has all to do with legislation, or the perception of the larger society, and also the fear of legislation that might come at some point. So the company that is the most prepared for that legislation to come will, of course, make the best profit. So companies are looking for ways to be more sustainable, not because it's perhaps not because it's the right thing to do, but because it might be profitable. And right now we're working with over 40 companies in 16 different projects, and there's about 20 or 19 of us from all around the world. And so this all has happened in the past 6 years, so that there really is a massive change, in my opinion. So what we do is we develop new products from wastes and industrial residues, or industrial side streams, as they are called. And so part of that is immobilization of harmful substances, for example, heavy metals and sulfides. There's something that's always present in natural materials, heavy metals and so forth. And it is just a matter of understanding in what form they are and making them in unreactive, basically, in order to be used in and in measuring the levels to be used in right applications. And so the industries that we work with are metal industry, mining, forest, energy, and construction. So basically all the biggest industries, and we happen to be in a good spot because we are surrounded by the sort of global players in each sector. So that makes us a good partner also worldwide. And so what we actually do is that the materials that we work with are things like slags, ashes, mine tailings, mineral wool, hazardous wastes. These are the starting materials. Then there's some processing step, and basically I think the deepest knowledge that we have is in the binders part, and that is because if you look at those waste volumes, those are massive volumes. And in order to make any dent, basically, to those, your application also has to have a large volume. And construction industry is the one with by far the largest volumes. For example, concrete is made more than all the other materials combined, and cement, which is part of concrete, so basically to make concrete you mix cement, water, and sand. And cement is the most made material. So those are massive amounts, and of course we are surrounded by cement. There's no way around it. We think about it as this mundane material, which it is, but it also has enabled the society to grow to what we now think of society. So there's we cannot really build a city without cement, as much as we perhaps would like to. But what we can do is we can turn cement into more sustainable alternative. So that's what we're working to do. And so that's what the binders means there. It is these inorganic, not usually people think of glues, which are organic, but this is inorganic, more cement type of binders. So basically there's hydration, alkali activation, then some additives to usual cement, and so forth. And the products are the construction material and so forth. So just a couple of case studies that we have done. The first one is, maybe I will go into a little bit deeper to that one because it's sort of a good example. This was 3 years ago when I got a call from my sister asking, do I know about textile waste? It was a big thing back then, and so I said I don't know that much about it, but I'll look into it and what we can do about it. And so then I started to look into it, and turns out it is a big problem. There are some amounts of it every year, and also there are companies that are interested that might use it, but really nobody was really willing to pay anything to do the research. So then I widened the scope a little bit. Then I thought of, is there some other fibers? What are all the fibers, sort of waste products in the economy that we could use to make basically to make a project in order to utilize those? And turns out there's mineral wool. That's the insulation material that we use in the buildings. This is probably also the outer walls, at least, made with mineral wool. And mineral wool is also beneficial product in the sense that over the whole life cycle, if you look at the CO2 emissions, that is saved because of the heating costs. It is by far positive. So it's a good thing to use those. But at the end, when you tear down the building, you have waste that you cannot do anything with it. So it turns out, even though it's very fluffy material, there's a lot of it. And it turned out to be the biggest fiber problem in Finnish economy, and it actually still is. There's no utilization route for it. And in Oulu, for example, in Oulu landfill, I work in Oulu. So in Oulu landfill, it is the biggest waste stream that still goes to landfill, because the rest of it you can burn, or you can get the energy out of it, or you can recycle it. But there's no utilization for this particular waste. So we had to invent a new process, and it turned out it is very good raw material for cement. And so we then published a few papers on it, and now we have worldwide interest in that material that we're working to find a company that will basically start gathering the material, processing it, and using it in different materials. So I thought that sort of gives a good overview of what's possible to do with these materials, or what we're looking to do. Then there's biomass ash. There's a lot of paper industry in Finland, and a lot of side streams that are burned, and what's left after that is basically the ash. And that's a good reactive material that's still not utilized, but hopefully in the future. And then mine tailings, which is one of the biggest ones in terms of size, or it is the biggest one in terms of the size. And then if you go a little bit sort of step further in the value chain, after mining, there is the metallurgical. If you look at metals, there's metallurgical processing where you process the material into the product that you know. And basically what it means is heating it up, melting it, and then removing all the sort of non-wanted elements. And that's what slag is. It's basically all the non-wanted elements. And of course, again, there's a lot of it, and some of them are utilized for the most part, such as blast furnace slag. That it is actually such a good product that there's, in some places, there's shortage of it for cement applications as well. But these other two ones are something that we actively work with. Then there are hazardous waste, municipal solid waste incineration ash is something that has a lot of, let's say, it has a lot of salts and different heavy metals that need to be taken care of. And synthetic gases, and the last one, which is perhaps closest to my heart, is the CO2 sequestration by using, in this case, geopolymers. And what that means is that we can make, there's actually no large-scale product existence that would contain CO2, that would actually have negative CO2 footprint. Of course, you can make biofuel, but again, that's not really a negative CO2 because you burn it and it's released. So cement is interesting also from that point of view because it's such a big volumes. We could be making cement that has some, let's say, 30% of CO2 in its raw materials, which means we would have a product that would have negative CO2 footprint. And in the long term, that would be a good solution. Right now, the one that we use, if you have a kilo of cement, it produces about 1 kilo of CO2 to the atmosphere. And of course, 1 kilo of CO2 is 1 cubic meter. So it's a huge amount of CO2. Every time you see something cement somewhere, you can think of it, 10 times more CO2 above it, or 1,000 times more in terms of volume. So what is it that enables us to process pretty much all the inorganic waste into cement? That sounds a little bit strange. The reason is that if you look at the chemistry of Earth's crust, this is the elemental composition, and half of it is oxygen. It sounds strange, but that's simply because these elements are in oxidized form. So it's not silicon, but it's silicon oxide, silicon dioxide. So there's most of the minerals are oxide minerals. And after that is silicon and aluminum. It turns out, I mentioned the word geopolymer earlier. Geopolymer can be made just from silicon and aluminum in about that ratio, actually. And by adding alkali activator, you can make cementitious products out of that. So what that means is that if there's any industrial processing waste, the high chances are that it also has the same composition that the Earth's crust in general, just because it's most of the processes are from crust minerals. So that's what enables us to use most of the biggest industrial waste streams into cementitious materials. And so what does it mean, the geopolymerization process? Here is, it's basically very similar to normal cement. So you have, this is biomass ash, then you have sand and water and alkali activator. You mix those together and you end up with the normal looking cement. And what happens chemically is the pH rises, it starts to dissolve these materials into their oxide form, and after the dissolution they will diffuse and then start to make longer chains, and when the chains grow long enough they become interlocked, and then that's when the material hardens and you end up with the regular cement. So there's a lot of chemistry behind a very simple, mix and get a hard product out of that. The geopolymer, this is actually made from geopolymer, some parts of this is in Australia. So it is a sort of process that is being commercialized around the world. And one of the sort of bottlenecks in that are the standards. Standards and also the uptake by the industry, because of course most of the industry there's cement industry that has a lot of interest of not to take this material into the market. So there's a lot of resistance there. So there's a long way to go, but we're making progress. Then I wanted to give you a little bit of scale of the material flows. So this is from Siilinjärvi. This is actually pure gypsum. So if you know those gypsum boards that are made for construction for inner walls, this could be more raw material for that. The only problem is that there's much more than can be used in the gypsum board industry. So there's massive amounts of this. And if you look at there's the guy and then there's the machine. If you zoom out a little bit, you still see the machine there. The guy is invisible, but it's we call this the gypsum mountain. This is something we haven't figured out a process yet, but we're in the progress. You can see some of the smaller ponds there as well for some other materials. Just to give you a scale. So then the second part of my talk, it's way out of my research. So it is more about the motivation of why do we do this. And so originally I was a physicist. Now I'm in the engineering, working as a chemist basically. So it's not really what I'm trained to do. But I believe this is work that needs to be done. And if you look back into the title of the talk, one way is to boil it down to what is the relationship between technology and sustainable development. And this was my first idea, was that okay, we're all together in a ship, we're traveling, we have a vague idea where we want to go, and technology has been something that has been powering us or propelling us to that direction. And I think this at least has been true for a long time. But in route to sustainability, there are a lot of difficulties, and so natural disasters can come from out of necessity, which used to be the case most of the time. Then out of incomplete knowledge. For example, if you take the earlier example of the oil, we didn't know that was actually a clean process, because of course if you compare it to horse manure on the streets, the cars were very clean alternative. There was no manure on the streets, and we didn't know that the CO2 would be warming the climate. And the third is out of neglect in the sort of societal level, not on an individual level, but more on the societal level. And I argue that more and more, or it seems to me that more and more it is out of neglect more than anything else. And of course the first one can be sort of cured by technology. The second one can be cured by more knowledge, so basically natural sciences. But what about the third one? That's the question. So maybe if you look on the systemic level of the problem, we can look at there's flows, and then there's actors that affect the flow. And if you, in any system, if you find the bottleneck where the flow is sort of restricted, and that's restricting the flow of the whole system, if you find that bottleneck and fix that, you could have a big impact on the whole system. So the question is, what is the bottleneck here? Is it technology? Is it natural sciences? Or is it something else? And to me, it seems that it's not technology. That technology is not any longer the bottleneck in this system. And one way to look at it is, or one big argument I think to me is, this is Moore's law. So basically, if in 1965, Mr. Moore was in a conference much like this one, and he postulated that every 2 years after this, the computers will double in speed, basically. And at that point, he had only 7 data points behind it, and it was really just a guess at that point. But it turned out that it was a self-fulfilling prophecy, and for 50 years after that, that became the truth of the industry. And this chart blows my mind every time. It's a logarithmic scale, and if you think about it, what it means, it used to be 1,000 transistors per whatever area. You can pretty much directly change that into speed. So the speed has been, it is now 20 million times higher than it was in the early 70s. So that is a huge change. And if you think about it, that's the reason why we have supercomputers in our pockets that are, communicating all at once. And if he had said that, okay, let's in 50 years have this in our pockets, nobody would have believed him. But because he had some vague direction, that was guiding the industry, that was sort of common vision. Everybody knew in the industry, in the chip industry, that in 5 years, if we don't have this fast computer, we won't sell any computers. So they had really strong incentive to develop the computers. And of course, because the computers were so powerful, they would have all the resources to do that. So this has been sort of self-fulfilling prophecy, but also it has enabled us to now have the personal assistants that we have. Well, the second reason why I think the technology is no longer a bottleneck is that technology itself doesn't change our behavior. The case in point is year 2007, when the first iPhone came out. And of course, Nokia was then the market leader by a big margin. And market analysts look at the phone and the specs, and then they reported to Nokia executives that yeah, you don't have anything to worry. You have much better technology than iPhone. And of course, what happened is that iPhone wiped out Nokia completely from the market. And it wasn't because of better technology. It was because of better design. So it's not technology that changes people's behavior. Of course, it's needed, but it doesn't change the behavior. So I argue that the picture is more like this. We have a bunch of different technologies, and somewhere inside there's the sculpture. We just have to find what is the right technology and what is the wrong technology, and maybe develop it a little bit further. But by and large, to me, it seems that we have most of the technologies that we need. Another way to put it, from prehistoric times, we have been inventing our way of different problems, I would say. And this is sort of the productivity gain that we have gotten from technological advancements. And it seems this is also a logarithmic change. And I think you probably heard the joke that if you have a hammer, everything looks like a nail. So I think this is sort of what we have now. We have been used to solving all our problems with more and more technology, but it seems that this time of the history may be different. So, what is different? I think we have reached the utopia, that we had the utopian vision. We wanted to go to the land of plenty, but welcome, we're here. I mean, we have everything that we want, but we're still not happy. And I think that's the sort of main issue. Yeah. So it's not one place that we want to go. And of course, if you look at utopias, what happens is that once you reach the utopia, it becomes dystopia. So it becomes sort of a dark version of itself. So now the question is, what is the next utopia? I think that's a good answer, good question for all of us to think about. Where do we want to go? But I don't think technology can provide the answers. Technology may be able to provide the answers, but not the questions. So we have to come up with the questions ourselves. So thank you.